Welcome to the Explainer. So, right now, one of the biggest upgrades in the entire history of the internet is happening kind of quietly in the background. It's this massive global race to rebuild the very foundation of our digital trust before it completely shatters. And look, this isn't some sci fi movie plot. It's a very real threat on the horizon, a scenario that cryptographers are calling the quantum apocalypse. The encryption that protects, well, everything, from your bank account to your DMs, is facing a total existential threat from a brand new kind of computer. So, what's the big deal? Well, here's the thing. Our current digital locks, like the super common RSA standard, are built on math problems that are just impossible for today's computers to solve. But a big enough quantum computer? It doesn't play by those rules. Using an incredible trick called Shor's algorithm, it could crack these problems, not in trillions of years, but maybe in a few hours. And the scary part? The threat isn't some far-off future problem. It's happening right now. Adversaries can be scooping up our encrypted data today, just stockpiling it, waiting for the day they can flick the switch on a quantum computer and read it all like an open book. Any secret that needs to stay secret for a long time is already vulnerable. Okay, so as you can imagine, this has kicked off a massive global race to build new defenses before the old ones are totally obsolete. So how do you defend against a computer that can break all of your locks? Well, you might think the answer is to fight fire with fire, quantum versus quantum. But actually, that's not it. The solution is called post-quantum cryptography, or PQC. And the whole goal here is to find completely new kinds of math problems that are just brutally difficult for any computer to solve, whether it's classical or quantum. We need a whole new kind of lock. And finding this new lock, it was no small feat. The U.S. National Institute of Standards and Technology, NIST, kicked off this global competition that went on for years. Dozens of algorithms were submitted, and then for years they were attacked, analyzed, and just completely stress-tested by the smartest cryptographers in the world to see what would break and what would hold. So after all that testing and attacking and analyzing, one clear winner started to emerge. A whole family of algorithms that stood out for their killer combination of security, efficiency, and just how versatile they were. The future, as it turns out, is being built on lattices. Lattices? Okay, so what in the world is a lattice? It sounds like something you'd find in your backyard, right? How can that be the key to our entire quantum-resistant future? So the core idea is actually super simple to grasp. A lattice is basically just a grid. You can picture a 2D one, like graph paper, or a 3D one, like a set of monkey bars. For crypto, we just take that same simple idea and stretch it out into hundreds or even thousands of dimensions that we can't even imagine. Right. But hold on. If it's just a simple grid, where's the security? Where's the hard part? Well, the secret isn't in the grid itself. The secret is a really, really clever trick about how you describe the grid. This is where the magic happens. It's all about a hidden trapdoor. Think of it like this. We have a secret map. We create our lattice using a good basis, a set of really simple, direct, clean instructions. That's our private key. But then for the public key, we publish a bad basis for the exact same grid, a set of really long, messy, roundabout instructions that totally hide that beautiful, simple structure underneath. So imagine you're the attacker. All you have is that messy, bad public map. You're basically forced to solve ridiculously hard problems, like this one, the closest vector problem. If I give you a point that's just a little bit off the grid, can you find the single closest point that's on the grid? In 500 dimensions, without that good map, it's considered basically impossible. But for us, with our secret map, it's easy. Okay, so we have this really cool geometric idea. But how do we turn that into something practical? An actual engine we can use for real-world cryptography? Well, instead of wrestling with pure geometry, modern cryptography uses this super clever algebraic trick called learning with errors, or LWE. Imagine trying to solve a puzzle, but every single clue you get has a tiny random mistake in it. Those little errors make finding the original secret almost impossibly hard. And it's been proven to be just as hard as those tough lattice problems. And from this one core idea, a whole family of tools popped up. Cryptographers basically built a whole toolkit of variations on LWE to get the right balance of security and performance, making versions with smaller keys or faster operations, but all of them built on that same rock-solid lattice-based security. And out of all those options, it turns out module LWE, well, that's the Goldilocks solution. It hits that perfect sweet spot, the best practical balance between the raw security of the original LWE and the super-fast performance of its cousins. It was just right. Okay, so this has all been pretty deep in the weeds of cryptography. Let's bring it back up. What does this actually mean for you, for me, and for the internet that we use every single day? Well, what it means is that we have brand new standards. The two big ones you're going to start hearing about are Kyber, which is for setting up secure connections. Think the little lock icon in your browser. And Dilithium, which is for digital signatures that verify something is authentic. These two are the designated heirs set to replace the systems that have kept us safe for decades. But, and this is a big but, the switch isn't exactly a walk in the park. The single biggest challenge? Size. These new quantum-resistant keys are way bigger than what we're used to. We're talking sometimes 20, even 40 times larger. And that's a huge engineering problem when you're dealing with systems that have limited space. But here's the wild part, the thing you wouldn't expect. Even though they're bigger, they are fast, like shockingly fast. The kind of math they do is just perfectly suited for the way modern computer processors work. So in a lot of cases, they actually run faster than the old crypto they're replacing. Pretty amazing, right? So you might be wondering, how do you even begin to roll out such a massive change without breaking everything? The answer is something called hybrid mode. For a while, when you make a secure connection, your device is going to use both the old, trusted crypto and the new post-quantum stuff. The final secret key is a mix of both. It's like a belt and suspenders approach. It protects us if there's some bug in the new stuff, and it protects us from a quantum computer breaking the old stuff. So yeah, this is not science fiction. This isn't some what-if scenario. It's one of the most important infrastructure upgrades in the history of the internet, and it is happening right now, all around us. We are in the middle of rebuilding the very foundations of digital trust to make sure our world stays secure for the quantum age and beyond.